Welcome back to part 7 of solving mazes with reinforcement learning. In this video, we are going to go ahead and build out this update parameters method, which is the method that actually does the learning in our reinforcement learning process here. So let's go ahead and start off by getting the necessary params. So we're going to pass in a memory, we're going to pass in a batch size, and we're going to pass in updates, which is a counter. We need to go ahead and pull our various batches from memory. So that's going to be state underscore batch, action underscore batch, reward underscore batch, next state batch, and mask batch, which is going to end up being our dones. And then we will do memory dot end little trick here. So if we want this to know what our what methods are available under memory, we can go ahead and import, so from buffer import, let's see, replay buffer. And then down here, we can actually tell Python that memory is of type replay buffer. And now, even though it hasn't been formally declared, we can say memory dot, and it understands what methods are available and what params those methods take. So now we get autofill on batch size, and we can say batch size. So not a bad idea if you are dealing with custom, variable types, to just go ahead and tell it what type it is supposed to be, and your IDE will be more helpful to you. All right, now we need to send all of these to float tensors. So I'm going to say state batch equals torch dot float tensor state batch, and then we'll just send it to self.device. And then this is going to look a lot like the next 4 lines. So we're just going to copy this 5 times and do action batch, reward batch, next state batch, and mask batch. All right. So those are all set. So just going to add a comment here. We are predicting the next state using, actually, I'm just going to say predictive model here, and give myself a to-do to add a predictive model. So this will be for our intrinsic curiosity that we're going to play with later, but that is not part of this just yet. So we're just going to continue down and say with torch dot no grad. We don't need to calculate gradients for these steps. We're going to say next state action, next state log pi, and we don't need that variable, is equal to self.policy.sample. And we're passing in next state batch. So we're basically doing the same thing that you would do to get an action out of the policy. We're just saying, hey, I'm going to pass you a batch of next states and see what you come back with. So we're going to say qf1 next target, qf2 next target equals self.critic target. And same thing, next state batch, next state action. So, we're allowing our critic to critique the actions taken by the policy network. And then we'll be taking the min qf next target equals torch.min of qf1 next target and qf2 next target. minus self.alpha times next state log pi. All right, and then we're going to say the next Q value equals reward batch plus mask batch times self.gamma times min QF next target. All right. Finally, let's keep going here. We're out of our with torch no grad block. We're going to say QF1, QF2 equals self.critic, state batch, action batch. So this was all focused on next state. This is now focused on current state. We're going to say QF1 loss is the MSE loss, the mean squared error loss between QF1 and the next Q value. And then we'll just copy and paste this and do QF2 loss is equal to F MSE loss Q2 of next Q value. So basically here we are comparing the values spit out by the critic to the actual next Q value with a discount factor applied. So that's what we're doing here. All right, go ahead and add a comment here. Update the critic network. This will help divide things up a little bit later. All right, actually no, down here, update the critic network. All right, and then we need to do QF loss. And this is just going to be a combination of the two before. So QF1 loss plus QF2 loss. So the total loss is what we're going to be working with. And then we'll do self.criticOptim dot zero grad, zero out the gradients, QF loss dot backward, and self dot critic optim dot step. Okay, we've now updated the critic. Now we need to go ahead and start working with the policy. So we're going to do pi and log pi equal to, and don't miss that I put an underscore there, equal to self.policy.sample. We'll pass in state batch and pi, and we're going to grab the, let's see, self.policy.sample. We're going to grab QF1 underscore pi, QF2 underscore pi equals self.critic state batch pi and min QF pi is equal to torch dot min QF1 underscore pi and QF2 underscore pi. All right. Now we can finally go ahead and calculate the policy loss. So the policy loss is going to be self.alpha times log pi minus the min QF pi, and we're going to take the mean, and the self.policy, we're going to do self.policyOptim.0 underscore grad, policy loss backwards, and self.policyOptim.step. All right, so what is alpha in this scenario? So alpha, I think I called it a discount factor, or no, I think I said that about gamma earlier. So alpha in this scenario is the temperature parameter, which in soft actor critic is your is what you're using for entropy. So the alpha parameter is basically trying to throw this calculation off just enough so that it's never just settling on a what it considers a perfect action. It continues to explore. So that is what that's for, and why we're adding that directly to our loss calculation for the policy. All right. Moving on, we can go ahead and take our alpha loss is torch.tensor 0.2 self.device. Alpha.t logs is torch.tensor self.alpha. And then we're almost done with this function. We're just going to get some output here. We're going to say if updates modulus self.target update interval is equivalent to 0, then we're going to do a soft update of self.critic target, self.critic with self.tau. All right, and then finally, we're just going to return all of the loss items here. So return qf1 loss dot item, qf2 loss dot item, policy loss dot item, alpha loss dot item, and alpha t logs dot item. All right, and we're returning all of these so that we can graph them. That's the primary motivator there. So when we get back over to main.py, we'll be doing some TensorFlow logging, and I want to have those variables available to add to graphs so we can see what's happening. My experience with really any kind of reinforcement learning, but especially when you start getting to these more complex environments with physics simulators, is that it tends to take a really long time. As in if you can get something done in a few hours, that's probably great. I frequently end up kicking off training runs, at the middle of the night and then checking back in the morning to see how it did. So you really want to log as much data as you can, because if you don't, you will end up spending 10, 12 hours of compute time and then not actually knowing what went wrong or being able to troubleshoot it. So that is my advice there. All right, let's go ahead and go back over to our main.py and just see if we can get our agent created. So first thing we're going to do is it's now time to add a whole bunch more variables that we're going to be using as we go through this. So we're going to have a replay buffer size equal to 1,000,000. I did 10 million, that's not what I meant. 1 million. We're going to do episodes equal 1,000. Later on, we'll bump that up, but for now, I really just want the first 1,000. Warm up equals 20. Batch size equals 64. Updates per step equals 4. Gamma is 0.99. Tau is 0.99. Alpha is 0.12, and some of these values are just defaults from the SAC paper. Some of them I have tuned very specifically for this problem. For example, this alpha parameter seems to work best with 0.12. You should definitely play with it, test it out, try these things yourself. So we're going to say target update interval 1, hidden size equals 512, and we've already got env name, and then that should be all for those parameters for now. All right, I can get rid of this critic line. We no longer need that. And it's time to go ahead and grab, we'll need a couple of parameters from our env. So I'm going to go ahead and grab observation info from env.reset. Okay, and I'm going to go ahead and run this. Let's just make sure we don't. Okay, we did get an error. Let's see. Why don't you like... Okay, attribute error, none type object has no attribute, get current context. SAC, exception ignored. I'm wondering if that's one we need to worry about for now. But I think it is. Let's see if we remove render mode human, if it's happy. There we go. Okay, it was a render mode problem. That's fine. We can worry about that later. Observation info equals env reset. So we're going to say observation size equal to observation.shape and the 0th element. And you'll see where we need these in a minute. Now we're down here for our agent. We can go ahead up at the top and say from agent import agent. And here we can go ahead and say agent equals agent observation size env.action space gamma equals gamma tau equals tau, and there are quite a few params here, but that is this is kind of where a lot of the magic's happening. So alpha equals alpha, policy equals policy. Oh, policy equals we have not declared a policy. So let's go take a look at why. All right, I don't actually think we need policy here for what we're doing. So I'm going to go over to our agent and find where we're setting policy and just remove it, because I don't think I think we're good there. All right, no more policy. Policy is an unneeded step for this implementation. So we're going to go on with target update interval equals target update interval. And in an ideal world, if we've named all these parameters right, they really should just be all parameter equals exactly the same name. I would prefer to keep most of those things as lined up as it makes sense to. So we'll do hidden size equals hidden size, learning rate equals learning rate. We did not set a learning rate. Let's go ahead up here and set one. Learning rate equals 0.0001. That is a very important hyperparameter. And then that is all for now. So let's go ahead and run this and just see if we get any errors. All right. It says we're missing one positional argument. Okay. We're not using exploration scaling factor yet, but I'm just going to go ahead and pass it in. We'll create a exploration scaling factor, and I'm going to make it 1.5, and I'll explain what this one does later. this is part of our Intrinsic Curiosity module, which we're just not using yet. All right, let's run it again. And we get our output running on CUDA. All right, so that's pretty cool. Let's go ahead and start with our, let's see, we're going to go ahead and create a memory. So memory equals replay buffer size, input size equals, why does it not, replay buffer is not defined. All right, from buffer import replay buffer. All right, there we go. So we've got input, let's see, input size equals our, what did we want to make that? Let me check. We're going to make input size equal to observation size. And actions is going to be env.observationspace.shape. All right. And we're just going to make sure that runs. And it's saying none type environment is not subscriptable. Let's see. It's not observation space, it's action space. All right, and our code is happy. This video is getting a little long, so I'm going to go ahead and end it here. In the next video, we are going to go and build out the agent train function and the agent test function, and then we can go ahead and start training.